Okay, so what is electrical power? Electrical power is the product of voltage and current. So P is equal to VI. Now let's see where we get this formula from. In the traditional sense, we know power is equal to work per unit time. Work done per unit time. Now in electricity, work is equal to voltage times charge. Q represents charge. Q is this charge. All right. Now, from this we have, substituting the values, we have P is equal to VQ over T. Again, current means the flow of charge per unit time. So I is equal to Q over T. Again, from this, by substituting this, we have VI. This Q over T becomes I. Like this, yeah. So finally we have P is equal to VI. That's how we get this formula. Now let's remove this. Now we have we can get some more formulas from this, some derivatives. So we can derive P is equal to, keep V as the same, and I, we can substitute the Ohm's law version of current. So V times I is equal to V over R in Ohm's law. So V over R is equal to V squared over R. So P is equal to V squared over R. That is another formula for power. Again, P is equal to, we can substitute V with the Ohm's law version. So V is equal to IR in Ohm's law. So IR times I. So we have P is equal to I squared R. And that is another formula for power. Now the unit of power is watt, alright? Watt or W. There's another unit, horsepower, HP. And there's a relationship between horsepower and watt. And that is 1 horsepower is equal to 746 watts, approximately. Alright. That's what we use for calculations. Now let's move on to electrical energy. Now electrical energy is the product of power and time. So W is equal to PT. We get this is a derivation of basically rearrangement of P is equal to W over T. So W is equal to PT. And what's the unit of energy? Unit of electrical energy is the same as the unit of work, which is joule. Now again, what is joule exactly? Joule is, we get it from here. So P is watt, right? And T is seconds. So watt second. Joule is WS, watt second. However, this watt second is a very small value, and it's impractical to use in real world scenarios. In the real world, we use watt hours or kilowatt hours. Kilowatt hours is usually the unit by which electricity is supplied to our houses. Now, efficiency. Efficiency is the ratio of output power or energy and input power or energy. So efficiency is equal to P output over P input into 100%. Also, we can use work or energy as W out over W in into 100%. They're the same formulas. And efficiency does not have any unit. It is a ratio. We usually express it in terms of percentage. This is the formula for cascading efficiency, or the total efficiency of a system that contains multiple machines or motors. To find the total efficiency, we do not add the efficiencies, we multiply them. So efficiency total is equal to efficiency 1 into efficiency 2 into efficiency 3 and ... And this multiplication is done in ratios, not in percentage. So if the efficiency was, say, efficiency is equal to 50%, and another was 60%. For cascading, we would do 0.5 into 0.6, right? Not 50% into 60%. Now let's move on to some practice questions. So this is a practice question for power. Let's see what we have. What power would be required if the maximum current draw was 50 milliampere for a 50 ohm resistor? So we have the given current. I is equal to 50 milliamps. 50 milliamps. And that is 50 into 10 inverse 3 ampere. And the resistance is R is equal to 50 ohm. What do we need? We need power, right? We need power. So we know from the first slide here, we have P is equal to I squared R, right? So we have I and R. So P is equal to I squared R. What's the value of I? The value of I is 50 into 10 inverse 3 in the SI unit. Ampere, we don't need to write ampere. Times resistance, so 50 ohm is equal to, let's calculate it, 50 into 10 inverse 3 times 50 is equal to 2.5. So 2.5 watts. That is our answer. Let's go to the second question in power. How much current is needed by a toaster labeled 700 watts and 250 volts? So we have power as 700 watt, and we have voltage V is equal to 250 volts. We need current, right? Now again, from the first slide, we know the base formula, P is equal to VI. So power P is equal to VI. Let's rearrange that for I. I is equal to P over V. And now substituting the values, we have 700 over 250 volts. And let's see what that comes out to be. 700 over 250. It's 2.8. So 2.8 ampere. That's the answer. Now let's go to energy questions. How much energy in kilowatt hour is required to light a 100 watt bulb for 1 day? Now let's see what we have. We have power, so P is equal to 100 watts. All right, and we have time, so T is equal to 1 day. But our unit of energy was either watt second or watt hour or kilowatt hour. So we have to turn this 1 day into either second or hour. Let's keep it in hour, just 24 hours. It's much more easier. And this is watt, 100 watt. So we need how much energy in kilowatt hours. So let's turn this into kilowatts. 100 watt is 100 into 10 inverse 3 kilowatts. So the energy required is W is equal to PT, equal to 100 into 10 inverse 3 times T is 24 hours, is equal to 100 into 10 inverse 3 times 24. We have 2.4 kilowatt hours. That is our answer. Let's go to the next question. Determine the total amount of energy used by a 50 watt lamp running for 12 hours and a 2 kilowatt lamp running for 50 minutes. Here, so we have two lamps. So for the first lamp, we have power of the first lamp is 50 watts, and time the first lamp runs for is 12 hours. All right, so what's the consumed energy or work done? W is equal to PT. So we have 50 watts, 50 times 12 hours. 12 is equal to 50 times 12 is 600 watt hours. 600 watt hours. All right, let's keep it at watt hours. So here we have P1, T1, and W1. Now let's go to the second lamp. For second lamp, we have again P2 is equal to 2 kilowatts, and that means 2000 watts, and we have time is 50 minutes, which means 50 divided by 60. We have 0.833 hours. 0.833 hours. So the energy consumed or work done is W is equal to P2 T2. So that's 2000 watts times 0.833 hours equal to 16 2000 times 0.833. We have 1666 watts, 1666 watt hours, right? WH. Now we need the total energy consumed or the total work done. So W is equal to W is equal to 1666, or W total is equal to W1 plus W2 equal to 600 plus 1666 is equal to 2266. Yeah, so 2266 watt hours. Let's turn that to kilowatts, if we may. So that will be 2.266 kilowatt hours. All right, let's go to the next question. Assuming the cost of electricity is 0.05 dollars per kilowatt hour, how much will it cost to light a 300 watt bulb for 3 days? So this is a cost question. Now for cost, the formula is pretty simple. Cost is equal to work done or energy consumed times the rate of electricity, price of electricity. Now we know that W is equal to PT times the rate is here 0.05 kilowatt per hour. Now this rate is in kilowatts, so we have to turn this 300 watts into kilowatts. That will be 300 times 10 inverse 3 kilowatts into time. Time is 3 days. We have to turn that into hours, so 3 into 24 hours, and then multiplied by rate 0.05. Let's see what we have. 300 into 10 inverse 3 times 3 into 24 times 3 into 24 times 0.05. So 1.08 dollars. That is the cost. Let's move on to the next question, efficiency. So what is the output power of a DC motor with an efficiency of 65% and an input current of 6 ampere at 250 volts? So let's see, we have efficiency, so eta is equal to 65%, and we have input current, IN is equal to 6 amperes, and input voltage, so V in is equal to 250 volts. So our input power will be P in is equal to V in times I in is equal to 250 times 6 is equal to times 6, which equals to 1500 watts. Now let's bring out the efficiency formula. Efficiency is equal to P out over P in times 100%. Now if we remove the percentage from here, from 65%, if we use the ratio, so that will be 0.65, then we don't have to use the percentage here. It'll be much easier for our calculation. So let's remove the percentage from here and we'll use ratios. So the ratio we have, efficiency is 0.65. 65% is 0.65. Sorry, 0.65 is equal to P out over P input, which is 1500 watts. We don't need to write watt. Alright, now in terms of P out, we have 0.65 times 1500 equal to 975 watts. 975 watt. That is our answer. Let's move on to the last question of the video. So if the efficiency of 3 motors is 50%, 60% and 70% respectively, what will be the total efficiency of a system comprising of all the 3 motors? So this is a cascading efficiency problem. Let's see what we have. We have eta 1, so efficiency 1 is 50%. We have efficiency 2 is 60%. And efficiency 3 is 70%. Alright. Now let's remember our cascading efficiency formula. So efficiency, total efficiency is equal to efficiency 1 times efficiency 2 times efficiency 3. Now this time, these values will be in ratio. So 50% will be 0.5, 60% will be 0.6, and 70% will be 0.7. Let's substitute the values. So 0.5 times 0.6 times 0.7 is equal to 0.5 times 0.6 times 0.7. It will be 0.21. 0.21. Now we multiply this with 100%. So we have 21%. Therefore, the total efficiency will be 21%. Answer. That's it.